तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we shall continue our discussion on the use of BiCMOS in larger systems, and we were as an example we were discussing the 32-bit adder, okay, and we said that this adder can be realized by using 8 4-bit carry look ahead adders, okay. So, you have a carry look ahead adders where you have A0 to A3 are the 4 bits as input, another 4 bits B0 to B3, you have the sum output S0 to S3, and the carry C0 is the comes in, and at the output you have C4. Okay, so this is a 4-bit carry look ahead adder. So, the advantage of using such a 4-bit carry look ahead adder is that this is, you see, it is a totally independent structure, and you can realize, okay, any multiple of 4-bit adders by just connecting a few of these 4-bit adders. Okay. For example, if you want to make a 16-bit adder, you just take 4 of them, okay, and just connect them together. Okay. So, this for the next adder, the carry in is actually the C4 and the carry out will be C8. So, but it is going to be a same structure. So, if you want 32-bit adder, you have to take 8 such adders and you just connect them together. Okay. So, that is very important even in the case of VLSI, okay, because the philosophy in VLSI design is that you require repeatable structures, okay, because it is very difficult to actually design every transistor in a VLSI. Okay. So, you must have structures which are repeatable. Okay. And so, this is a very is a totally repeatable structure which you can go on adding, okay, to obtain for example, a 32-bit adder or even 64-bit adder or any any multiple of 4-bit adders. Okay. So, here we saw that we had already seen the structure, and we had seen that this is the most critical path, okay, that is the carry C0 to C4 path. Okay. So, we have to, because this is the when you have 32-bit adders, you have 8 such adders, and this C0 must propagate all the way to the last adder, okay, in order to obtain the full addition. Okay. So, this is a very critical path, and the delay in this path must be reduced as far as possible. Okay. So, the carry propagation circuit, the so called carry propagation circuit must be fast enough. Okay. And we have also seen the expression for this carry output here. Okay. What is it? We have C4 is equal to either G3 plus G2 P3 plus G1 P3 P2 plus G0 P3 P2 P1 plus C0 P3 P2 P1 P0. Okay. That is basically what are the G's and P's? Gi is equal to Ai Bi, and Pi is the exclusive OR of Ai and Bi. Okay. That is, this is called the generate term, that is if A and B are both high, then you generate a carry, okay, and Pi is the propagate term, that is if the Ai Bi, I mean one of them is 1, then only the output is 1, okay. That is if you have a carry input, okay, and one of A or B is 1, that means there is going to be an output carry. So, basically you propagate the output carry, propagate the carry, that is whatever is coming in as input, if the carry input is 0, the output will also be 0, carry output will be 0. If the carry input is 1, the carry output will be 1 if Pi is high, okay, Pi is 1. So, you propagate the carry, whatever is the carry input is propagated to the output. So, here C4 is high if you have generated the carry in the bit 3 term, alright, then C4 will be high, or if G2 was high and it was propagated through P3, or G1 was high, that you generated a carry in the bit 1 stage and it was propagated through bit 2 and bit 3, or it was generated at G0 and it was propagated through bit 1, bit 2, bit 3, or there was an input carry, okay, which was propagated through all the stages, okay. So, this is the equation, okay, which has to be realized in order to obtain this, okay. Now, the circuit which is generally used, this is a very popular circuit, okay, called the carry chain actually. So, which is realized to generate this, okay. What we want to do here, we want to see here is how to use bipolar transistors as well as the commonly used circuit using MOS transistors together with the commonly used circuit using MOS transistors to obtain higher speed, okay. So, just let us look at the circuit for this, okay. Yeah. So, the circuit is something like this. I think I will just write it like this: G0 P2 P1 plus C0 P3 P2 P1. Okay. Now, the circuit is something like this. We have MOS transistors mostly here, okay. So, those of you who are familiar with this circuit using MOS transistors, this looks quite similar, okay. Okay. All right. So, basically what you have is, this is a clocked circuit. So, you have say phi 1 clock. So, this should go low when this is G3, when G3 is high, then this line should discharge, or P3 G2, or this is P3 G2 discharging, P3 P2 G1, or P3 P2 P1 G0, or P3 P2 P1 P3 P2 sorry P1 G0 P0, this is C0, okay. Now, the difference between this circuit and the CMOS circuit is that you have a bipolar transistor here, okay, and you have some MOS transistors here, okay. So, this is phi 2 say, all right. So, these are certain MOS transistors with certain fixed gate voltages, all right. So, this is VDD. Okay. Now, the circuit works like this. This is a BJT, output bipolar transistor. Now, when phi 2 is high, okay, phi 2 and phi 1, okay, there are two phases of the same clock. Okay. So, when phi 2 is high, phi 1 is low, and phi 1 is high, phi 2 is low. Okay. So, when phi 2 is high, what happens is phi 1 is low. So, if phi 1 is low, that is all these MOS transistors are off. Okay. So, there is no path, okay, for the charge to discharge here, base charge to discharge. Okay. So, this N block, the entire block is off basically, it is not connected to ground. Okay. Phi 2 is on. So, there is going to be a base current for this transistor, all right, and so this MOS transistor acts as a load resistance basically. Okay. So, this transistor is going to have a base drive, the output is going to be low. Okay. And care is taken, one has to design it properly, so that the load, this effective collector resistance and the base resistance is such that the transistor does not go to saturation. Okay. If the output is low enough, but the transistor does not really go to saturation. Okay. All right. There is another transistor here. This transistor actually provides a small base current, okay, usually of the order of in this particular design which I am talking of. Okay, this one is say approximately say 16 microamperes. I will just give the reference where they have talked about this. So, this is around very small current, constant current is provided. I will come to that why you require constant current. So, in the phase phi 2, when phi 2 is high, you basically output is low. So, this is the pre-charge phase as it. Okay. Now, what happens is when phi 1 goes high, all right, phi 2 goes off. So, this base current is off, this phi 2 is off, phi 1 goes high. So, all these MOS transistors turn on. Okay. So, this transistor is going to turn off if there is a discharge path to ground. So, there will be a discharge path to ground if G3 is high, or P3 G2 is high, or P3 P2 G1 is high, or P3 P2 P1 G0 is high, or P3 P2 P1 P0 C0 is high. Okay. Now, what happens is this, okay, so even if this is not high, so the output should remain low. Okay. But because the transistor is going to discharge, basically the charges are going to recombine in the base of the transistor. So, this transistor is going to go off, okay, shut off. So, there is a small 60 microamperes current maintains the transistor in the on state. Okay. Of course, if this discharge path is there, okay, this current will flow through the discharge path and the transistor is going to be off. Okay. So, this small current is used to retain the transistor in the on condition. All right. So, what is going to happen is, so normally if it was a CMOS circuit, you would have a CMOS inverter here. Okay. In place of that, you have a bipolar transistor. Now, what is the advantage of having a bipolar transistor here? The advantage of having a bipolar transistor here is that this voltage along this line, okay, at this point say, all right, the maximum voltage you can have is around 0.8 volts or so, okay, because that is the base point of the transistor. Okay. You cannot have more than say 0.8 volts, okay, the VBE of the transistor. Okay. So, the voltage swing on this line is limited to around 0.8 volts, whereas if you had a CMOS inverter here, okay, the voltage swing would go all the way from 0 to 5 volts, okay, and obviously that would take more time. Okay. So, here by limiting the voltage swing, you are increasing the speed, okay, because the capacitance has to charge only through a smaller voltage, whereas if you look at the output of this circuit here, the output voltage goes all the way from 0 to 5 volts. If VDD is 5 volts, the output voltage will go all the way from 0 to 5 volts. I mean not exactly 0, but close to 0 to 5 volts. Okay. So, this output voltage has a full swing. So, this output can drive the input of the next stage, that is, okay, if you have the series of these inverters, okay, of this 4-bit carry look ahead adders. So, the output of that can be fed in as the C naught of the next 4-bit carry look ahead adder, because it is going from close to 0, which means that that is going to be less than the threshold of this particular MOS transistor, and when it is 5, it means that the transistor is going to turn on. Okay. So, whereas on the output side you have the full swing, when the input side the voltage swing is less, and also because of the larger current drive capability of MOS of the bipolar transistors, you get a higher speed. Okay. So, you see that basically here BiMOS, you are using a BiCMOS, but it is not in the form of actually a BiCMOS gate or anything, okay, but we have just replaced, okay, a CMOS inverter by a bipolar transistor. So, in fact, there is only one bipolar transistor in the entire circuit, which consists of so many MOS transistors. Okay. So, basically the area requirement is the additional area requirement is very small. Okay. It's almost the same. Okay. Very you are not using many bipolar transistors, but you are just judiciously using required number of bipolar transistors, but the amount you gain out of that is tremendous. So, I'll just refer to this paper, okay, from where I took this circuit, okay, this P. Hota and others, IEEE Journal of Solid State Circuits, volume SC 21, number 5, pages 808 to 813, October 1986. Okay. So, this is actually a paper from Hitachi Corporation in Japan, okay, and this was the first, they claim the first BiCMOS microprocessor, okay, which they fabricated. It was back in 1986, and of course, they have subsequent papers, okay, where they have improved the performance, okay, but this is the original paper, and many of the concepts are actually given in this paper. Okay. So, this is one circuit, and they have made a comparison also. Okay. Well, they have used they have compared with CMOS, and they have added, you know, FF, 8 Fs with 0 0 0 0 0 1, this particular addition, okay, where the carry has to propagate all the way. Okay. For CMOS, it took 20 nanoseconds. Okay. For BiCMOS, that is just using one bipolar transistor in the circuit which we have shown, okay, it took just 7.2 nanoseconds. All right. So, you can see the amount of improvement one can get. This is for a 2 micron technology, okay, at that time. All right. So, you can see the amount of improvement one can really achieve, okay, by judicious use of bipolar transistors in basically a CMOS environment. Okay. So, you make a BiCMOS, okay, all right, it's you just have to introduce bipolar transistors in critical paths, okay, where you can speed up the operation, and you get a tremendous improvement, okay, over the corresponding CMOS. So, basically it is the CMOS environment, but you just introduce bipolar transistors wherever necessary. Okay. All right. So, this is one example of use of BiCMOS. I shall also give another example, also from the same paper, where they again, as I said, they were discussing the microprocessor chip they had fabricated, okay, BiCMOS microprocessor chip. Well, an important component in a microprocessor chip is ROM. Okay. A random is a read-only memory. Okay. A read-only memory is used in a microprocessor to store the micro instructions. okay, that is basically the whatever instructions you have, and then to generate the control signals, okay, which is going to activate the different parts of the circuit. Okay. So, it is stored in the ROM. Okay. So, that is because it is read only memory, you know, is just meant for reading. You cannot alter the memory whatever is stored there, and in a microprocessor, since the instructions are fixed, okay, there is no need for changing them. So, you actually use a read only memory. So, again we just take it up and see how use of BiCMOS, that is bipolar transistors, together with again the basic CMOS environment, actually improves the performance. Okay. So, in that particular chip, okay, the ROM they used was a 2K into 64-bit ROM. Okay. That is, there are 2K words, okay, and each of them has a 64-bit wide. Okay. The information stored in each word is 64-bit wide. This is actually true for any of these micro-coded controllers. Okay. That is, usually these bit lengths are very wide in this case. Normally in a memory chip, okay, you won't have this type of wide bit, the 64 bits or so. Okay. But anyway, we will just discuss this. Okay. So, now, so 2K into 64-bit ROM. So, how many bits of memory are there? 2K would correspond to 2 to the power 11, and 64 is 2 to the power 6. Okay. So, 2 to the power 17, okay, cells. All right. So, you must have a memory which can accommodate, all right, so many bits of information. Okay. So, the basic structure of this memory is something like this. You have an address decoder. So, you have the address inputs, sorry, doesn't come. Okay. You have address decoder, then you have a driver, okay, and then you have the array. Okay. So, this is the memory array, or cell array. All right. And this array, the output goes to some buffers, okay, and from here you have the outputs here. Okay. In this particular case, what happens is, in this where you stored microcode, because any instruction, okay, may have more than one cycle. Okay. So, the output part of it is fed back again to the next address input. Okay. So, you have a multiplexer, okay, which either takes entry address, a new address, or a few this, in this case 11 bits, okay, because it's 2 to the power 11 will be fed in as input here, okay, to the address decoder. All right. So, this is the basic structure. Anyway, so what we are interested in is the memory. Okay. Now, so how do you have a ROM memory as such in this case? What you have is, you have the output of the drivers. Okay. Now, you are having 2 to the power 17 cells here. Okay. Now, one we would like to have a sort of square array. Okay. All right. Now, one way would be to have a 2 to the power 11 lines here, okay, and you have 64 bits. Okay. That means we would have a very much a very rectangular type of array. Okay. And but this is not good enough, because this means that this side or the lines, okay, would be the data output lines would be very, very long, because you are having 2 to the power 11 lines here, okay, and that would mean a lot of capacitance. Okay. So, basically to reduce the capacitance, the bit line and the word line capacitances, we would prefer to have a square array. So, if you have 2 to the power 17 cells, we would like to have the array say 2 to the power 8 into 2 to the power 9, okay, is 2 to the power 17. Okay. So, what is done is you basically have 2 decoders here. Okay. So, one is you have 2 to the power 11 address lines. Okay. So, you take 2 to the power 8. Okay. This array will be 2 to the power 8 into 2 to the power 9. So, you have 500 2 to the power, you have 512 columns, okay, and 256 rows. Okay. 512 means 2 to the power 9 and 256 rows, okay, 2 to the power 8 rows. All right. So, what you do is you have 2 to the power 8 rows here. Okay. So, one decoder will have will be an 8 to 2 to the power 8 decoder. All right. So, the address, okay, 2 to the power 11 address lines, 8 of them are decoded to give 2 to the power 8 lines here. Okay. So, another 3 of the address bits are again decoded to give 8 lines. Okay. There will be another 8 of them. All right. And this, so here what you have is you have 64 into 8 columns. Okay. You have 64 into 8 columns. So, depending on one of these the 8, okay, the 3 into 8 decoder which you have, so they are used to choose one of 8 columns. Okay. So, basically what you have is you are going to have a multiplexer here for every 8 columns. Okay. You have a multiplexer. Okay. So, this multiplexer chooses one of 8 columns. Okay. The output of that multiplexer is the one of the 8 columns. All right. So, you have 64 into 8 columns. So, you will have the output which you get here is 64. Okay. So, basically again just to repeat, you have 11 2 to the power 11 address lines, 2 to the power 11 locations, okay, addresses, each going to have 64 bits of data. Okay. Now, what we have, in order to make it square, we make it 2 to the power 9 into 2 to the power 8, 2 to the power 8 rows. So, you have 2 to the power 8 rows here. So, there is a decoder 8 to 2 to the power 8 which is going to, so the output of that 8 into 2 to the power 8 decoder is going to choose one of the 2 to the power 8 rows here. Okay. And so, there are 64 into 3 into 8 columns. Okay. So, there is another decoder 3 into 8 decoder, okay, which uses the remaining 3 address lines, and it makes one of the 8 columns, one of the 8 output lines of that decoder is high. So, it chooses one of 8 columns. Okay. So, you have 64 into 8 columns. So, at a time you choose basically one column. All right. So, there are 64 output lines. Okay, fine. Now, how do you so that is clear now. Now, basically again we come back to the topic which we were discussing, that how does bipolar transistor help in improving the speed. So, basically in this ROM, in each of the intersection of the rows and columns you might have a cell. Okay. So, what is the cell like? So, basically if you have an intersection here, okay, the cell consists of a MOS transistor which is something like this. So, this is connected here. All right. Okay. So, in another location, okay, this may not be connected. Okay. So, here the gate of this MOSFET is connected to the word line here. Okay. Now, what is going to be the difference? Basically what is going to happen is, suppose you pre-charge this line. If this line is pre-charged, okay, Now, if this is connected, okay, and when this input goes high, okay, this MOS transistor is on, this MOS transistor can discharge this line, okay, whereas if it is not connected here, this MOS transistor is not going to discharge this line. So, this line is going to remain high. So, depending on whether this connection is made or not, you are actually storing a 1 or a 0 in that particular location, okay, all right. So, if you have a MOS transistor which is connected, okay, you are able to discharge that line. So, that line voltage here go to 0. If the MOS transistor is not connected, you are not able to discharge that line, and so the line voltage is going to remain at 1. Okay. So, what is done is, so this is clear. So, now what is done is you have a pre-charge circuit. Okay. Now, this pre-charge circuit, so I will just take one of the columns, consists of bipolar transistors. Okay. In fact, in that they use a Darlington pair type of configuration, okay, to pre-charge the lines. Okay. Now, obviously, because of the larger drive capability of the bipolar transistors, okay, once you have this line capacitances are very large. Okay. For this particular circuit, they have the word line capacitance is 8 picofarad is the word line capacitance, and 3 picofarad is the data line capacitance. Because these lines are very long, you see, there are going to be so many transistors here. So, if you have 512 columns, so on this line you can have 512 transistors. Okay. So, these capacitances are very, very large. Okay. So, this is the word line, this is the data line. So, the word line capacitance is 8 picofarad and the data line capacitance is 3 picofarad. So, if you want to pre-charge, you have to pre-charge this capacitance. Okay. So, how fast you can pre-charge depends on how much current, okay, you can drive, okay, to charge the capacitance. Okay. So, for larger drive capability, you use bipolar transistors here to pre-charge the bit lines. All right. And then here at this end you have a similar structure just like the previous case, okay, where we discussed this carry chain. Okay. Similar structure like that, that is, you are basically driving a bipolar transistor. Okay. I just draw it like this. Okay. This is a bipolar transistor. So, it is coming to the base of a bipolar transistor again, all right, and then again you have as load, you have the MOS transistors, just like the previous case. All right. So, this is all right. So, again, and this is the output here. Okay. So, this output is coming here to the base of the bipolar transistor. Now, what is the advantage here? Again, this bit line voltage, the maximum voltage it can have here is around 0.8 volts. So, when you are pre-charging or discharging the bit line, okay, the voltage on that line is limited to voltage swing on that line is limited to 0 to 0.8 volts. Okay. So, you do not have to charge or discharge the capacitance. Okay, this is a very large capacitance to a high voltage, through a high voltage, whereas if this was a CMOS inverter, it had to go all the way from 0 to 5 volts. Okay. So, that is the advantage, the voltage swing on this line is less. Okay. So, you can have faster operation. Okay. Whereas the output voltage here can go all the way from 0 to 5 volts, almost 0 to 5 volts. Okay. So, there is no problem. Okay. And also, so here the bipolar transistors are used for pre-charging and also at this output here. Okay. So, this is just like a BJT inverter, okay, the bipolar inverter here. All right. So, we have used a bipolar inverter here, as well as in this particular circuit for the driver also we have already seen that a bi-CMOS is going to be very good as a driver, okay, because of the fact that they can drive large capacitances, okay, because you are using the bipolar transistor again. All right. So, we have already seen that when you compare with a CMOS with a BiCMOS, okay, the BiCMOS has got the variation of delay with large capacitance is going to be much less. All right. So, it is capable of driving large capacitances because the word line capacitances are quite large. Okay. So, here again you use bipolar transistors in the driver stages. Okay. So, here the output, okay, is actually from bipolar transistors, okay, here. All right. So, these are the 3 areas where you use bipolar transistors, okay, and let us again look at the results, okay. So, as given in this paper. So, ROM access time. So, memory delays are usually in the form of access times, where access time is the time you get the output, okay, after you have floated the address. So, it is greater than 30 nanoseconds for CMOS, okay, and it is 17 nanoseconds for BiCMOS. So, this is for 2 micron technology, okay. For 1 micron technology, okay, it is 9.2 nanoseconds for BiCMOS 1 micron. Okay, so you see that, well, again the comparison is with CMOS, and you see that again with judicious use of bipolar transistors, okay, one can actually reduce the delays tremendously. Okay. So, in fact, the next topic which we will take up for the next few classes is memories. We shall also see the advantages of using BiCMOS, okay, compared to CMOS. Okay. So, the different memories here again just give an example that bipolar transistors, okay, are very much useful in reducing the delays in memories. Okay. And so, BiCMOS as such, where you use bipolar transistors judiciously to improve the performance, okay, that is basically to reduce the delays, okay, or improve the speed. Okay. And here also another thing is, you do not if you look at it, okay, the total number of bipolar transistors is going to be very much smaller compared to the total number of MOS transistors. Okay. Just use a few bipolar transistors, okay, I mean judiciously. Okay. It is not that you are using equivalent number of bipolar transistors. So, actually the area is not going to really affect the area as such, okay, by much, but at the same time you extract a lot of advantages. Okay. So, that is about this topic on BiCMOS, okay, where we have seen the advantages of where BiCMOS has the advantages of, it retains the advantages of CMOS. At the same time, by introduction of bipolar transistors, the bipolar transistors, when you compare with MOS transistors, you know, they have some certain specific advantages. That is the larger drive capability of bipolar transistors. That is they can drive much larger currents. Okay. If you compare with bipolar and MOS transistors, because of the fact that bipolar transistors are vertical, the current flows in a vertical way instead of compared to MOS, where the current flows in a horizontal direction along the surface. Okay. So, bipolar transistors can provide lot of current. Okay. In equivalent MOS transistor, if you want to fabricate an equivalent MOS transistor driving the same current, the size would be huge. Okay. Whereas in a bipolar transistor, it actually can provide lot of current. Okay. At the same time, you also know that the transconductance of a bipolar transistor is much higher than that of a MOSFET, because of the fact that in a bipolar transistor it follows the exponential relationship between the input and the output. Okay. That is, the output current is proportional to the exponential of the input VBE, exponential VBE by VT. So, only a small change in the input voltage is required to make a very large change in output current. Okay. Whereas in the case of MOS transistors, it is a square law relationship. Okay, so the GM, the transconductance is very low. So you actually require a small change in input voltage to make the large change in output current in a bipolar transistor. So that is the advantage. So if you are the input line, you know, is having a large capacitance, okay, because the bipolar transistor, the input voltage variation requirement is much smaller, okay, you can the time required is going to be much less to change the input voltage, okay. So that is the advantage, okay. So that for all these reasons, okay, BiCMOS as such, okay, has a lot of advantages, and it is used extensively in modern circuits, okay, where the problems related to technology has been removed, okay, because previously the problem was that CMOS and bipolar, it was difficult to fabricate on the same wafer, but once that problem has been removed, people take advantage of both the advantages of bipolar and CMOS and make BiCMOS circuits and realize better and better circuits, okay. Okay, so that is about BiCMOS. The next topic which we shall take up is memories, okay. We have been mostly discussing logic families and gates, etc. But now we shall just move over to larger systems as such, where memories, okay, form a big chunk of the circuits which are being fabricated now, the large scale integrated circuits, okay, and we shall take that up. And in that also we shall see the advantages of both the different types of memories, that is we shall take up the static RAM, the dynamic RAM, then the ROM, okay, and we shall also see how each of these cases, for example static RAM, you just have the CMOS circuit or the BiCMOS, how it is going to be better, okay, or in where you put, I mean if you make a BiCMOS static RAM, where you are going to introduce the bipolar transistors, okay, and how does it really improve the performance of that particular memory, okay. So these are some of the things which we shall take up the next few classes. Just I'll just give you a block diagram of a memory chip, okay, just as an introduction. I think so a memory chip consists of, so you have the addresses, okay, you have the address lines, okay. So which so a memory will have some addresses, okay, and in each address there will be some data, okay. So suppose you say that you have a 2K into 8-bit memory, okay. So this refers to a 2K addresses, okay, that all right. 2K is actually 2 to the power 11, okay, 1K is 2 to the power 10, okay. So 2 to the power 11 memory locations, and each of them you have an 8-bit information, okay. So now memory chip would consist of the address inputs, again this address inputs are fed to so suppose let us consider a memory which is a 1-bit memory, okay, that is a 2K or say a 1K into 1-bit memory. So this would consist of 2 to the power 10 addresses, all right, and each of them has 1 bit, okay. So what is done generally is you have, now if you require a decoder, you basically require a decoder, okay, because the address will be in the encoded form, so that in 10 bits, okay, and each of these combinations refers to an address. So you have to decode it, okay. Now if you use a 10-bit 10 to 2 into the power 10 decoder, you will have at the output 2 to the power 10 lines, okay, they are far too much. So what you do is you do a 2-dimensional decoding, that is you have 2 decoders each of 5 bits. So you have 2 to the power 5 decoder, one 2 to the power 5 decoder, and another 2 to the power 5 decoder. So you have just so many lines now instead of 2 to the power 10 lines. So it's just 2 to the power 6 instead of 2 to the power 10. So that is the advantage. So you have an X buffer, and then you have a decoder. All right, the output of this decoder. So if you have 2 to the power 10, okay, so this you have 5 lines, say. So here the output of the decoder you will have just 32 lines, okay, and then you have the memory array. Okay, all right. So you have an array, and then this is the cell array. So the memory cell, each cell stores 1 bit of information, okay, and then you have another set of similar Y buffer, then Y decoder, okay, and then you have what is called a sense amplifier. Okay. The sense amplifier is used to sense whatever information is stored in that memory, particular memory locations. So here you have 32 bits, okay. If it is 5 here, you have 32 bits. So here you have a sense amplifier. So basically you, for each of these columns you will have one sense amplifier, okay. So here you have this array which is 32 into 32, okay, and each of these intersections, all right, you have a cell. At each of these intersection you have a memory cell. So you have 32 into 32 memory cells. So it is 2 to the power 10 cells, okay, storing 2 to the power 10 bits of information. So you have a sense amplifier for each of these cells, and so basically what is done is the Y decoder does a multiplexing operation sort of, okay, and it you choose one of these columns, okay, the output of one of these columns. The X decoder, what it does is it chooses one of the rows, okay, so it activates just one of the rows, okay, out of these 32 rows, okay, and so in each of these columns only one row is activated. So at each of these columns output, what you get is the information corresponding to that particular row which was selected. Now what you do is here you choose one of these 32 columns, so that basically you are choosing one particular cell, information corresponding to one particular cell, okay, and this output, whichever output is there, goes through an output buffer to the output. And then you also have a control block, okay, which is fed to the sense amplifier, which actually gives, you require information like whether you want to read or write and all sorts of and these sort of information, okay. For each of them you have to generate the particular control signals which is going to, okay, drive all these different circuits, okay. So you have a, so basically this is the block diagram of any memory, okay. So you have, again just to repeat, you have an X buffer and a Y buffer, okay. You have 2 to the power 10 memory cells. So you have 10 address bits. So you have 5 here, 5 here. So you have 32 rows. You are selecting one of the 32 rows, and here you are selecting one of 32 columns, and each at the intersection of each row and column you have a cell. So corresponding to that, the sense amplifier, if you are reading, the sense amplifier is going to sense what is there in that cell and you get the output. If you are writing, okay, it must be able to write, okay, if the write signal is high, okay, you must be able to write into that particular cell, okay. Now of course if you have, now here what you have done is a 1K memory. Now suppose you want to have 1K into 16-bit memory, what do you have to do? You are going to have 16 such memories, all right. Of course the problem is if you have 16 such memories, you know, this is going to be again a rectangular array. So what you can do is, if you want to have a square array, all right, you can do is, you can basically again, that means you are going to have 16k cells now, 1k into 16k cells. Okay. So what you do is, instead of 5 address lines, okay, you can have 7 address lines here, all right. Okay, you are all right, and then that means you have 2 to the power 7 columns, 2 to the power 7 rows, okay, and so you will also have 2 to the power 7 columns. Okay, so basically giving you 16k, all right, and then you again have to multiplex or choose, or basically you get for each block of 16 columns. Okay, so you get a 16-bit information, all right. So you can have, that way you can make a square array. Okay, so if basically if you know how to make a 1-bit memory, okay, you can reproduce it, okay, generally to make a 16-bit memory. Okay. So these things we shall discuss in the next class. We shall see the different types of memories, that is, whether it's a bipolar memory, or if you want to make a CMOS memory or a BiCMOS memory. Okay, and each of these are basically ways of realizing the memory, but also we can look at static RAM, dynamic RAM, and for all these cases, okay, we shall look into how to realize them, okay, using these forms.